Hello and welcome. We have another session. Again, my name is Matt. I use any pronouns. These, incidentally, are Gladys and Daryl, my little snakes. So, just so that you know everyone's name. Now it's my pleasure to introduce to y'all Reuven Lerner, who's going to be speaking to us about the PyArrow revolution in Pandas.
Hey everyone. So, yes, we're going to talk about the PyArrow revolution in Pandas. Just a few words about myself. I teach Python and Pandas. That's my full-time job. I've been doing it for many, many years. I do corporate training, but I also have a whole online platform at lernerpython.com. I have newsletters, including a newsletter about Pandas and data analytics. Every Wednesday, I send out questions based on current events. This week's topics were airport and airline delays, which have been a little bit in the news. And on Thursdays, then I send out the solutions with the Jupyter Notebook. That's at Bamboo Weekly. I'm on YouTube. I write books. You can come find out lots more. I've got a booth here. I'm one of the sponsors of this conference. You come talk to me, get a fancy red t-shirt. But let's start off with a basic idea in programming, dry. Don't repeat yourself. Don't repeat yourself. So if you have the same code on multiple lines, then you don't want to repeat yourself. You're going to use a loop. And if you have the same code in multiple places in a program, well, don't repeat yourself. Use a function. And of course, if you have the same code in multiple programs, then don't repeat yourself. Use a library. And of course, in Python, we call these modules or packages. And a module, as we like to say, helps the future you. Right? It means that you don't have to work so hard in the future. It also means that other people can avoid repeating your solutions. They can just take what you've done. And so we've got Pandas, and Pandas is fantastic because it means you don't have to implement your own data analysis routines. And so if you use Pandas, the hard stuff is done for you. Reading data, cleaning data, analyzing data, visualizing data, writing data, all this stuff is done for you. And it's super, super convenient, and that's why it's popular. So Pandas has been around for a while already. Wes McKinney invented it back in 2008, and he built it on top of NumPy. Why would you do that? Because NumPy is stable, it's fast, it handles 1D and 2D data, it has lots of different data types. That is fantastic. And so I often think of Pandas as the automatic transmission instead of the stick shift of NumPy. That's just super, super convenient to use. Right, so we've got a Pandas series, which is basically a wrapper around a 1D NumPy array. And we've got a Pandas data frame, which is basically a wrapper around a 2D NumPy array. Or, if you prefer to think of it this way, it's kind of like a dictionary of series. So the thing is, this brings lots and lots of good news. NumPy storage is in C, so it's way faster than Python, and it uses way less memory than Python. It's also vectorized, so things execute really quickly. And it comes with tons of analysis methods. So again, you don't have to repeat yourself, you don't have to work hard. And it's used by many, many, many people and projects, so you know it's stable. That's the good news. The bad news is that storing data in Pandas via NumPy uses lots of memory. And its storage, even though each sort of Pandas column is its own NumPy array, it still has to do this dance between rows and columns because at the end of the day, NumPy is storing things in rows. We store the data exactly as it is, so there's no compression, there's no zero copy techniques. It's not really designed for batch processing, it's not designed for streaming. And complex data types, forget about it, right? Strings, sort of, kind of, almost. Dates and times, they do work. Nested types, no. So memory usage, not so great. Or great if you're in the memory business, right? So if we read in a 2.2 gigabyte file, and this is one of my favorite data files to work with, it's New York City parking violations back from 2020. So we read this in, and it's not the biggest data, right? But it's pretty big, it's 12.5 million rows. And I say, well, how much memory is that using? And I say, df.info, tell me how much memory that uses. And I'm told 4.0 plus gigabytes. I'm like, plus? Plus? I spent a lot of money on this computer. It's telling me plus? Aren't you a computer? Can't you compute how much memory it's using? And the answer is, oh, you want to actually compute how much memory it's using. You have to tell me that explicitly. Right? Oh, it's actually using 15.6 gigabytes, which I think we can all agree is roughly 4 gigabytes, right? So basically, this is a bit of a problem and it's annoying. And it's because when we store strings in pandas, what's happening is that it's storing a pointer, pardon the obscenity, it's using a pointer to point into Python memory where we have a string. And so in order to calculate how much memory we're using with those strings, for each of those individual strings, it has to go follow the pointer, go into Python memory and ask it, and that takes a lot longer. Not to mention Python strings are potentially big. So we've got Arrow, which is dry for data, right? I know, you probably think your data at work is already dry enough. We'll make it even drier. And so basically, there are many packages, languages, and frameworks that work with two-dimensional data. So what if we had one library that everyone could use, right? Don't reinvent the wheel. That's the whole idea of dry. We have a working data structure. What if we use columns explicitly, internally, and all sorts of other places for our fast retrieval? We could reduce the overhead of moving data between different systems and even take advantage of modern processors. Because remember, NumPy and Pandas, wonderful as they are single-threaded, single-process. They can't take advantage of the modern hardware. And of course, there are lots of packages that try to do this and get around it, but fundamentally, that's where we're at. So Arrow's been around for quite some time, right? 2016. It's already on version 20, released just like last month. And so you can use Arrow. But you can also use PyArrow, which you might be able to guess from the name, is the Python bindings for Arrow. And you can use these directly in your programs, right? So you can create arrays, which are one-dimensional. You can create tables, which are two-dimensional. You can retrieve different rows and columns, sorting and grouping. And Arrow provides the kind of data types that we are used to in the Pandas world. It has primitive types like ints, floats, dates, times, timestamp, strings, very useful, binary. It has dictionaries, which are kind of like Pandas categories. It has maps, which are kind of like Python dictionaries. Why? Whatever. I'm sure there's a reason why that doesn't quite map up. Complex types. It has arrays like Pandas series, tables like Pandas data frames. That is great. PyArrow is great, but so what? And so the thing is, we are, right, this talk is the PyArrow revolution. Pandas is moving toward using PyArrow. Some of the functionality is already here, and lots more is coming in the future. Using PyArrow can save you time and memory. And as of Pandas 3.0, it will be required. So you're already like sort of encouraged to think about this. So I'm going to divide this talk into like 3 different parts of this revolution that you can think of and worry about and take into your own work. Part 1, faster CSV reading and writing. Right, we use lots of CSV files. When I started doing data stuff, I was like, well, obviously, we are going to be using these really sophisticated binary formats to sling around our data. And obviously was doing a lot of the work in that sentence and was also wrong because we use CSV everywhere. And it's really flexible and useful and popular. Also, poorly specified. Or everyone can sort of, what was it? I think it was Andrew Tannenbaum who once said that the great thing about specifications is that everyone can choose the one that they like most. And that is sort of what's happened with CSV. It's like, oh, I'll just try this and this and this. It's also slow because it is a textual format. So we have to read it in, or Pandas needs to read it in, and then figure out what kind of values do I have in each column. Now we can speed this up by saying which D types we have explicitly. We can speed it up by saying low memory equals false, which means that we will load the whole thing into memory and it'll analyze each column as a whole as opposed to in little chunks. But it's still really slow. And so the solution is use PyArrow for reading and writing CSV files. How? It is super simple. You say engine equals PyArrow and read CSV, done. Is it really that useful? Let's find out. So I've got a function here that loads up that data file of New York City traffic tickets, right? And I'm going to sort of figure out how long it takes to do this. And I'm going to say read CSV with file name. I'm going to say low memory equals false. Read the whole thing into memory. And then I've got a similar, almost identical function where it's going to load it in using PyArrow. So what are the results? If I load it the regular way, it takes 103 seconds on my computer. With PyArrow, 8.6 seconds. So, the good news, it is 10 times faster. What else do you need to know? Like, it's just really ridiculously faster. Here's the other thing. It's faster in many ways because it does read the whole thing into memory. So you don't need to worry about this whole low memory equals false thing. Also, here's another little bonus. PyArrow detects date time columns automatically. So you don't need to specify parse dates when you read in from CSV, hey, these columns are in a date format, assuming it's in a decent date format, otherwise you do have to use date format. Bad news, some CSV files are a little too weird for PyArrow, and if the file is really small, like, who cares? So it's like, it's the sort of thing where if it's small, no one cares. If it's big, everyone cares. And so you can use this today. It has been in Pandas for a while. Why not just make it your default for loading things up, right? Now, it doesn't always work, but it usually works, and so that's worth looking into. Okay, part 2, faster file formats. Right, I already mentioned that most of our data nowadays is in CSV, or you might have heard of this esoteric little program called Excel. And so, yes, Excel is a binary format, but it's like, it can really get kind of messy. And I actually had something in Bamboo Weekly just a few weeks ago where basically we were reading in from Excel, and it was ridiculously, ridiculously slow. And someone explained to me, well, that's because Excel files are like zipped XML files, and like everything that was involved in opening up just made it like horribly, horribly slow. So Arrow actually defined 2 new columnar binary formats. There's Feather, which is faster reads and writes, but does not get compressed, and Parquet, or Parquet, I cannot figure out what it's supposed to be. Someone can correct me afterwards, please. All right, slower reads and writes, but it's highly compressed. So it's like the whole time versus space thing. So the same file in CSV was 2.2 gigs, in Feather was 1.4 gigs, and with Parquet was 379 megs, right? Way, way smaller. And they were both of these formats were way faster to load. Now, why were they faster to load? Because it's already in a binary format. So we don't need to guess, right? Pandas doesn't need to load it and say, does this look like an int? Does it look like a float? Right? You can just do it. We don't need to say. And other languages and systems also support Feather and Parquet, which means that you now have this data interchange format that is binary and cross-platform. Now, how much faster? Yeah, a lot faster, right? So one file that I read in here took nearly a minute in CSV with a core Python engine. PyArrow took 11.8 seconds, so like 12 seconds. Feather 10.6, Parquet took 9.1, right? Like, once again, reading it in is way, way faster in these formats. It's faster in the binary formats than it was in the textual format, and you know exactly what you're going to be getting. And you can be storing it. Instead of in 64-bit, you can use 32-bit or 16-bit, right? You can really specify and then crunch it down even more. So you can use these formats today. You can also, and I've heard of many people who do this, they read in the data in CSV once, right? Like they go out for a very long lunch, come back and it's done, and then they save it to Parquet or Feather, and then like no longer can they take lunch at work, but at least it's working faster. This is terrible, by the way, if you are paid by the hour. Okay, third part of the PyArrow revolution, swapping out NumPy, and this is really, really big, or at least it will be big. It is currently in Pandas. You can use this, but it is experimental. That said, at some point in the coming years, this will become the default. I mean, I trust the Pandas core developers that basically they will sort of be very sort of slow and thoughtful about this. They won't just one day cut off NumPy, but little by little, we're going to be encouraged to use PyArrow. So it's going to take time. And already today, you can specify in read CSV or in several of the other read methods, dtype backend equals, and you can say PyArrow. And so if I do this, if I say I'm going to use PyArrow in the backend, now I can do this myself, by the way. I don't have to say dtype backend equals that. I can just say, right, PyArrow dtype equals, and usually that's whatever dtype it is, and then I put PyArrow in square brackets. So for example, here's a series, right? I've got some integers in there, and I say dtype equals int64 of PyArrow. That's my dtype. I can also say, here's a data frame, and I'm going to use this dtype here, right? It works just fine. If I want, I can even convert one column in my data frame to use PyArrow dtypes. So I have here from that traffic ticket data set, vehicle color and memory usage. How much memory is it using? 635 megabytes. So let's now redo that as type string PyArrow. How much is it using now? 134 megabytes, right? That's a big savings for a trivial amount of work, right? And for those of you unsure about this, that's right. We're now using 20% roughly of the memory that we did before. Well, I can do this, as I said, when I read in a CSV. I just say engine equals PyArrow, and then I say dtype backend equals PyArrow. And when I read this in now, if I look at the dtypes, and you can squint and maybe see it, all of these are now PyArrow dtypes. Or I can just say, hey, dfinfo, tell me what my dtypes are. And it summarizes them for me, and it says, oh yes, you have 15 PyArrow int64s, 25 PyArrow strings, and 3 PyArrow nulls. Nulls? What does that mean? Well, it turns out that if you have a column where every single value is NA or NaN, it's like, well, why should I store this? I'll just store a count, and I'll say this is all null, done. And so we see here that 100% of these values are NA, and so why store it even? And the memory usage does indeed go down a lot, right? From NumPy 15 gigs to PyArrow 3.7 gigs, saving an awful lot of memory. Yeah, but we don't care about memory, right? We care about how fast it is. Like, that's how we show off to our friends, our nerd friends at least, right? So let's say I want to find out the top 5 values in a column from this parking ticket thing. Okay, so I can use timeit. Timeit is great. It comes with a Python standard library. Inside of Jupyter, I can use timeit with 1% sign, and then it'll time the line that I've got. So here, you can just pretend it's all in one line. If you use 2%, then it does the whole cell. And so I want to find out what are the top 5 vehicle colors that were ticketed in New York. And we see, okay, that takes 216 milliseconds. All right, what if I do it with PyArrow? And you can see here I have NP, df of NP is the NumPy version, df of PA is the PyArrow version. And that takes 107 milliseconds. That's right, it's about twice as fast. And for those of you have tough time with math, you can even see the colorful graphs here. Oops. No, come back. There we go. Now you can see the colorful graph. Okay, right, so you can see it's much faster. What if I want to do something a little more ambitious? I want to search in strings with regular expressions, right? So I'll say here, I want to know which vehicle colors included the letters B or Z. Okay, well that's gonna force it to work a little harder, right? By the way, I'm sure that's the sort of query that everyone involved in traffic is interested in, right? So this takes 2 seconds to run. Okay, it's gonna push its limits a little more. What if I do this with PyArrow? And here also, it is taking way less time, 366 milliseconds, right? Graphically, we can see PyArrow, which is always going to be in the red here in all of these graphs, much faster. This is time. So like PyArrow is just like way faster, right? In fact, here it's like 5.5 times faster. What if I want to do something else? I want to know what states have blue cars. You've always been dying to know that, right? So I say here timeit, where vehicle color equals blue, and right, then I'm going to say registration state value count. So I'm going to grab that. This is a little more complicated with my dot lock. And so we find here, I can do that on NumPy version. I can do the PyArrow version. And it's going to be 10 times faster, right? 300 milliseconds versus 36 milliseconds, right? PyArrow is just like doing really well here. But that raises the question, is PyArrow always faster? You know what the answer is, right? And so what if I say here, I want to find out, right, issue date, so when was the ticket issued? I want to grab the month out of that. I want to find out in which month did people get the most tickets. So this here in NumPy gives me 148 milliseconds, and in PyArrow it gives me 151 milliseconds. Basically the same. Not bad, right, but no great shakes. But here's the interesting thing. I gave a version of this talk last summer at EuroPython, and this was the graph I got then. So we can see that PyArrow is improving a lot, right? So before, 9 months ago, 10 months ago, PyArrow took something like a quarter, 25% longer than NumPy, and now they're at parity. And that shows the sort of work that's going into this system, why also it's going to take a little while until it's all standardized and so forth. What if I want to find out what were the most common states whose license plates were ticketed in March and July? I know this has been keeping you up at night, right? So basically, they'll take 205 milliseconds. It'll take 179 milliseconds. Once again, we see that the difference is not that great. PyArrow is a little better, for sure, but here's how it was 10 months ago. PyArrow used to be longer. So we see that things are improving where they weren't so good. How about something else? It's a little more challenging, grouping, right? So if I want to group how many feet on average from the curb were people parked, depending on the state they were from, right? So we do that for both NumPy and PyArrow. We see PyArrow is now, again, a bit faster. It's like, 30% faster there. So that's pretty good, right? We see that these are improvements. But remember that PyArrow assumes that you were doing a lot of work by columns. And so the moment that you start using rows, it's a little different. And by a little different, I mean a lot different. So I'm going to use .iloc. right? Those of you who are used to pandas know that there are two ways for us to retrieve by the index. One of them is .lock, which uses the actual index names values. The other is .ilock, which does it by position. So here I'm saying I don't care what the index is in my data frame. I want to retrieve from rows position 0, 100, 100,000, and minus 10,000. And that works. And it takes 43.2 microseconds. I do the same thing with PyArrow. It takes 366 milliseconds. Not quite sure what that is? Yeah, remember that. 366 milliseconds to 366,000 microseconds. Here's the graph, right? There is a blue line there, I promise you, but it's really, really small. Okay, well, what if I say, okay, I'm willing to deal with that, but I'm going to use .lock instead. I actually want to use the real index, as it were, and .lock is always slower than .ilock, or almost always slower. So we have 82 microseconds, 406 milliseconds. Once again, right, we see this incredible, incredible distance between PyArrow. It's just taking far, far longer than the NumPy version is. Well, let's do something a little fancier here, right? What if I use .lock with a lambda? This is the way I like to do it nowadays. I know it's all like scrunched up here. I couldn't get it to fit on the slide better. I'm very sorry. But like method chaining is really nice. You put it over several lines, except here it's not so nice. But at least it works. So if I want to find out, like, feet from the curb and the mean, right? So 3 seconds to do this versus in PyArrow 2.45 seconds. So like PyArrow is faster, certainly, right? But it's not, again, a panacea. Here's something that's even wilder, right? What if I want to do a self-join, right? Joins are something that we do when we have multiple data frames. It's like in SQL, multiple data frames, and I want to get one large data frame back. So I'm going to say I want to join df of np to df of np. So basically it's just going to like do a self-join there. And okay, that takes 11 seconds. What if I do it in PyArrow? 102 milliseconds. Let's just show off that graph, folks. Right? PyArrow takes more or less 0 time to accomplish something that takes a painfully long time to do with NumPy. And once again, last year, 10 months ago, this is where PyArrow was. There has been a dramatic improvement in the performance here. And so overall, remember that the blue lines are NumPy and the red lines are PyArrow, right? The blue lines are almost always, not always, but almost always longer here. And we've seen this progression over the last number of months even, of it getting even better. So PyArrow as your backend, possibly a great idea, but remember, it is officially experimental, right? So if you lose all of your company's data, don't say you heard it from Reuven. Okay. I'll name some other speaker who I don't like. No. All right. New and different behavior. So a few things that you should also know about PyArrow. First of all, let's create a series. 10, 20, 30, 40, 50. D-type is int64. I insert a nan in there. And now we get nan in there. And now we get a D-type of float 64. Why? Didn't I want integers? Yeah, but nan is a float. So it forces the conversion to float. So, nullable types. If we use PyArrow types, and I even assign nan there, it doesn't have to be NA, look at this. I get something different. I get something called NA. This is the same as nan, but it's not a float. So it doesn't interfere with the stringiness, as it were, of our D-type, and it remains in 64. It does not need to be converted to floats. And this is not only string, as I said, I was getting ahead of myself. This is not just for ints. This is for strings too. So if I have a string series and assign nan there, no longer does it get turned into object. This stays NA, and this stays a D-type string. This is huge, and this is great, because otherwise you would end up with these, in the standard version, current version, you would end up with basically object, and it's just annoying. How about this? I'm going to set up a series of int8s, 10, 70, and 100, and I add 100 to them, and I get not quite the right answer. Why? Because it rolled over. I said int8, right? And as we all know, computers do what you tell them, not what you want from them. And so it added 100, and there were int8s, and so it overflowed. What if I add 1,000 to it? Well, here I get an error. It says, wait. I can't add 1,000. 1,000 is beyond the int8 region. But if I set it up with D-type of int8 in PyArrow, that's a different story. It automatically gets promoted to int64. Amazing. And if I add 1,000, okay, int64 can handle that too. So this behavior has changed dramatically thanks to PyArrow in the background, and it works great. Now I want to add, this is different from the extension types. right? There are different types in pandas that we call extension types, and those are nullable, yes, but otherwise they're just sort of wrappers around these same NumPy types. They're still row-oriented, they're still Python strings, still no compression, still not interoperable with other systems. And here's something that I just learned in the last few months. This is kind of cool. In the future, of course, strings will be handled by PyArrow and it'll be great. But what if you want strings now to be handled by PyArrow? You don't want those Python strings. You want them to be small, you want them to be fast. You can say PD options future infer string equals true. And when you do that, all of your strings will be in PyArrow. This means that they are faster to create, faster to allocate, faster to load, and far less memory usage. Now you could use PyArrow directly, right? If you want to just use it as a data structure, you can. And if and when you want to, PyArrow has this great method called toPandas. Voila, we get a data frame back. Or you can do the opposite. You can say, I'm going to take my table, or I'm going to take my data frame, and I'm going to get it into a PyArrow table. And when our backend uses PyArrow, right, DFPA values, we get back a NumPy array. So don't be surprised if you ask for .values and you get back a NumPy array. That's the behavior because that's the way it's been set, but it still is PyArrow in the background. So right now, Pandas is pretty powerful, but I think it's no longer a powerful package. I think it's increasingly becoming a powerful platform with these swappable backends, and it's even getting swappable front ends, right? We've got things, right? We've got an API that we can use that Polars and others are sort of using. And we also have things like DuckDB. We have things like FireDucks that sit on top of Pandas and use it as its sort of data source. Bottom line, PyArrow is already revolutionizing Pandas. You can get faster file loading today, faster, more efficient backend storage tomorrow. You can even try it today. And Pandas is becoming more and more of a platform. And PyArrow is part of that move. And pretty soon, you'll be able to choose how you want to store your data and how you want to retrieve your data at a variety of different levels, keeping Pandas there in the middle. All right, I think we have a few moments for questions. Thanks so much. I would love to talk about this more. Come see me at my booth if you can't catch me after the talk. Thanks so much.
Suppose I'm doing a bunch of calculations on data frames, using just Pandas data frames and using like NumPy math. Is swapping out, and I'm doing this primarily like vectorized column operations for the math. Is PyArrow going to give me a substantial increase in the performance of those calculations?
My guess, my gut feeling is not so much. Just because the numbers are going to, like the math is still going to take the same amount of space, right? It's mostly where you have strings that you're going to see the dramatic difference in storage. I'm guessing it would be pretty much on par.
Okay.
It could be though, it could be if you are pulling things out by row. The moment you start doing that, if you're just doing like one series times another series or something more sophisticated, then I think it'll be pretty much the same. The moment you say, oh, I want only these rows times these other rows, then it's going to take a hit, at least for now.
Okay, thank you.
Hi. Hi, thanks for the talk. So you actually touched upon it on the end that there's alternative backends, alternative front ends coming, so like DuckDB, Polars, and a lot of these are built from the ground up to use these modern techniques like Arrow. So I'm confused as to what Pandas' role is in this new ecosystem, because I've started using IBIS, which is using DuckDB in the backend, and it seems to sort of replace Pandas, and I'm familiar with the Pandas sort of like API. So it's hard to migrate to a new platform, but at the same time, I'm not seeing any particular value that's intrinsic to Pandas.
So look, I think it's like not a new thing that sort of over time we've figured out better techniques, newer techniques, right? So Pandas is at this point, while it's amazing and wonderful, it's also kind of like a legacy technology. And so the real advantage here, I think, is that you get to keep your use of Pandas, keep the same API. You swap out the backend in favor of a new one, and voila, you save tons of time and tons of memory. You don't have to go through that painful process, and the larger your organization, the more painful it is of vetting something new, learning a new API. If you're starting 100% from scratch, and you're willing to go with, shall we say, like a smaller community, less support and so forth, then one of the other options might be more attractive. But I think so many people, like it's a ridiculous number of people who download, install, and use Pandas every day. And to tell all of them, guess what? You should really switch to something else. I mean, that's fantastic if you're a consultant and less fantastic if you're the company using it.
Hello. So I wanted to ask, it seems that NumPy is good in some cases, and then the PyArrow is better in other cases. Is there a tool that allows us to distinguish when is one tool or backend better than the other?
Ooh. Not that I know of. I mean, I think what it comes down to is, for the most part, like when I started playing with PyArrow in Pandas, there were a whole bunch of methods, especially string methods, that would give you an error saying not supported, right? Like it's just not gonna work, you get an exception. That I've not seen in a while. So they've filled in a whole lot of gaps, and now we've seen even here that they filled in a bunch of the performance gaps. The big remaining performance gap is the whole row-oriented thing. If I wanna pull out certain rows, so I think that's sort of the heuristic you can use for determining whether it'll be slower or faster. And from what I understand, it's mostly because, again, a data frame stores these NumPy arrays in its columns, but it has really gotten fast at turning that back into a 2D NumPy array so we can get the rows from it. I have to assume that like the people, like the core Pandas developers, know about this and are working on it, and we'll get that soon. But like, that's sort of the more you are doing row-oriented stuff, the more that NumPy is still going to be advantageous to you. All right, thank you so much.